Welcome to Short Talks from the Hill, a podcast from the University of Arkansas. My name is Hardin Young, and I'm a writer here at the university. Today, I'd like to welcome Jill Marshall, Assistant Professor of Geosciences. Marshall describes herself as both a geomorphologist and a critical zone scientist. She's also part of a team that recently received a $256,000 grant from the NSF to study the effects of climate change on Arctic watersheds. Jill, welcome to Short Talks.
Thanks so much, Hardin. I'm happy to be here.
It's great to have you. We'll start with a couple of softballs. What is a geomorphologist? What is the critical zone?
So they're related in many ways. Geomorphologist is geomorphology is a branch of geology, and I study the surface of the earth. So things like how rivers shape the earth, how landslides shape the earth. Part of my research is how trees shape the earth. So it's the near surface of our earth and the processes that shape it. So that's the geo, the earth, and the morphology, the shaping part. And the critical zone is a thing. It's a real thing. It's been in existence as long as we've had plants and water on Earth, but it only really became a scientific discipline in the early 2000s. And that's when scientists who were working on this thin skin of the earth where soil meets rock began to realize that it wasn't just about geology, and it wasn't just about hydrology, and it wasn't just about rain, atmospheric conditions, but all those things together shape this zone. And the zone is defined as where vegetation intersects the troposphere, the very lowest part of the atmosphere, and then all the way down through the soil, through the weathered rock, and down to where life stops, where you have fresh bedrock. And so you have these zones of the top of the fresh bedrock, the weathered rock. I'm speaking as a geologist. If you talk to a microecologist, of course, they would describe it with a different framework about where the tiny critters live. But the soil and all of these things, the vegetation and the atmosphere, when one changes, like if the amount of snow that lands on the trees or the timing of that snow, or if it's snow versus water, that controls what the ecosystem is. It controls the weathering engine, like how those plants might intersect with the rock and weather it chemically or physically. And it controls how deep the weathering zone, how much water, how much porosity there is to hold water and carbon. So all the things that we depend on, like the soil where we grow our food and the water that we depend on, is stored in this critical zone.
Much of your research examines how fast mountains break apart and turn to sediment. What are some of the ways you do that?
Well, I just briefly touched on one of them, and I'll touch on two. So one thing I study is the mechanics of how trees, when they're inserted into rock near the surface of the earth, of how they damage that rock, open it up with cracks, and eventually turn it into disaggregated rock or sediment. So turns out that it's not just things like when the wind blows and a tree moves back and forth in the wind, and you can imagine those big roots cracking open the rock as they move, but when trees take in water at night, their roots swell. And they do this over and over and over. During the day, the roots shrink as that water goes up to the top of the tree where it intersects with the troposphere, right? And so every day, that tree is tapping on the rock. And it turns out those little tiny taps, given enough time, can actually begin to change the porosity, how much void space there is in those rocks. So that's one direction. I go the other direction, from life to no life, and study how ice breaks rock apart, but not glaciers. This is in settings where there aren't glaciers. It's just very, very cold in the wintertime and warm in the summer. And that sets up a process where even when temperatures are below zero, the water stays liquid and it moves through the rock and it gathers in cracks. And it's that gathering of water, that flux of water as it moves, it presses on the cracked tips and breaks the rock apart.
Speaking of tree roots, you actually insert sensors into the roots, don't you?
Well, I try not to hurt the roots. I always am apologizing to the trees, but I use these super cool, very novel sensors. So they're about the size of a woman's fingernail, and thinner than a fingernail. So, a little bigger than a dime, about maybe. And I insert those into the place with the root rock interface. And so I have to have a root that's big enough, which is generally about an inch or so in diameter, a couple centimeters or bigger. And we put those little things in, and they will measure everything from a tiny tap to about 1,000 pounds force. So, but we have those combined with sensors that measure when does it rain, when does the wind blow, and we can use all of those combined to understand what environmental conditions are leading to the rock pushing, the tree pushing on the rock.
And how long might a sensor like that, be underground attached to a root?
I've had them for up to several years. If we were doing this on video, I'd show you a picture of one where the sensor itself surprisingly survived, but the little wires that attach to the sensor didn't do so well because they're under a whole bunch. The wires get moved around, animals come, the wind blows. They're not at all designed what I use them for. These little sensors were originally designed for dental implants, for understanding like how much force you press down with your teeth, and for prosthetics. So if you're going to build an artificial limb, you want to be able to give a signal back to when that limb is touching something and exerting force. So I've totally repurposed them. And they've been really, they're not designed for what I use them for at all. So they're not so great for actually saying what the true force is, but temporally the wind blows and 2 years later, that signal is still showing up from the sensor, and we're collecting the data at 10-second intervals. So they're sitting there embedded in really harsh, outside for long periods of time.
Okay, so let's move on. I mentioned your recent grant from the National Science Foundation. Can you tell us a little bit about the project?
Sure. It started, if you don't mind me telling you a little bit of background that leads to the project. So it started with a very small grant to my collaborator, Marissa Palouse. She had a NASA grant to go to this place that's far north of the Arctic Circle. It's in the Northwest Territories of Canada at 68 degrees north. There's a small mountain range just to the west of the Mackenzie Delta. And she picked this site because it was a potential really good analog for Mars back when Mars was cold and frosty. And so you don't need the whole long story of how I got involved in the project. Huh?
Is she an interplanetary scientist? Is that why
she's an everything scientist? She's amazing. She's another geomorphologist. She studies debris flows, and she does a lot of work also on Mars. She's actually part of her PhD work involved driving the rover, so making decisions about where it should go for collecting samples for us geomorphologists back on Earth. And so I went there as part of that project, and we just through a series of conversations and mutual interests, we decided to put in to study a couple small watersheds, the one we were at and another one, that were well studied in the 70s and 80s. So we already have some information about these watersheds. And what we're doing is what's called a source to sink study. So we're looking at how sediment is produced, so breaking solid rock and turning it to loose rock, and then how it's transported and sent downhill. And our hypothesis is in that this really spectacular region that's one of the fastest warming places on Earth, in the Arctic, that you've had a shift in both how fast you can break the rock apart. So in this case, as it's gotten warmer in the winter, you have more time that is less cold. So it used to be really, really cold for much of the winter, but it creeps up into the negative 15 degrees C range, which I'm sorry, I don't even know what that translates to into Celsius. I'm terrible, or into Fahrenheit, but it creeps up into this negative 15 degrees C range, and this frost cracking window when this liquid water can break rock apart is about -3 to -15 degrees C. So we think that sediment production is sped up. You have basically endless supply of sediment. At the same time, it's warmer in the summer. You have more rain on snow events. You have a longer period where this ground isn't completely frozen, and which means, and you have more water, so you can move sediment a lot faster. So we think it's transitioned from sediment moving downslope in a slow flow, if you want to think of it that way, creeping and sediment lobes moving down, to having big debris flows and landslides, which are a hazard. And also, this rapid of a change has really big implications for aquatic ecosystems. When an ecosystem doesn't have time to adjust to really rapid changes.
Yeah, it sounds concerning. What are some of the challenges of working in this environment?
This summer will be the mosquitoes. We'll be there in July. I've been told they're ferocious. But in general, with any remote location, not just the Arctic, I think there's two big challenges. One is that you have to be prepared. Like, you cannot forget a screwdriver that you need. You need everything with you, because there is no corner store that you are going to run to. In this case, there's a challenge with just space, because if you go in with a helicopter, you have to decide what is the absolute necessary thing you need to bring. And then finally, any remote field work, your equipment, once you set it up, it's at the mercy of hoping it survives till you come back. You could have a big wind event, you could have a curious muskox. So you could spend a week getting some instrumentation in, leave, and the next day have something destroy your carefully constructed instrumentation station. And you won't know that until you're able to get back out there a year from then.
And I assume you're staying in tents or something out there?
Yeah.
Yeah. Okay, we're almost out of time, so I'm going to ask you one final question. What is a book you read recently that you would recommend?
Oh gosh, it's not a hard question. I just have I'm in the middle of reading Hamilton. That's taking quite a long time.
That's a big book.
Big book. This is a fun old book. It's called Calculus for Cats. So, and one reason I would recommend it is, despite being a college professor, I went to community colleges. I returned to school in my late 40s, and so my math background is surprisingly spotty. I'm good at learning what I need to learn, but it's been fun for me to go back to the basics. So if you want to go back to the basics on calculus, fun books like Calculus for Cats are the way to go.
Jill Marshall, thanks for talking.
Thanks, Arden.
Music for Short Talks from the Hill was written and performed by local musician Ben Harris. For more information and additional podcasts, visit Arkansas Research. That's arkansasresearch.uark.edu, the home of science and research news at the University of Arkansas.